Hello, everyone. We're just going to take a moment to allow folks to join in. Just give it another minute before we start. We have a very packed agenda today. Hey, well, welcome everyone to our second forum as part of the International Institute for Sustainable Laboratories Circular Economy for Labs Community of Practice. This is on water reduction and reuse in labs because we are getting ready to celebrate World Water Day this Friday, March 22nd, a day to sort of respect and ensure we have clean water around the globe. So we'll talk about how to save this precious resource in our laboratories because we may be wasting it in more ways than you know. Before we get started, I just want to go over a few housekeeping items for the webinar today. There are a lot of folks who registered, so everyone's muted to minimize background noise, but you are able to submit questions in the Q&A box. We will have a panel and time for questions at the end. And if anyone really wants to share something they're doing to save water in your lab as well, let us know. We might be able, if we have time, to unmute you and have you participate in the conversation. But for now, I'll put those questions in the Q&A box as they come up. And we will record this presentation. So if you know someone who couldn't make it today, or you just need to leave early, that will be on our community of practice website. We will send a link around to everyone who registered. And if you are having any problems hearing us, just put something in the chat, the Q&A box, and Michaela will help you. So just to go over what we're going to do today, we have a number of short presentations. We're trying to leave as much time for questions and answers. But we'll talk to you a little bit about what the community of practice is, some I2SL updates, and then we're going to hear from a representative of EPA's WaterSense program. They have a best practice guide that they helped create in conjunction with I2SL. And Robert Pickering, my colleague at ERG, is going to give us some of the highlights of that with regards to labs. And then we're going to hear about some very specific efforts in 3 different universities to reduce water use. The University of British Columbia, we'll hear from Kate Andrews, who is trying waterless condensers, but developed a lending program so they could see how they work first. Star Scott from the University of Georgia is going to talk about their autoclave education program and what they do when they get a solenoid valve leak and some of the lessons learned. And finally, Patrick Murphy from Vanderbilt Engineers will talk to us about a project at Lehigh University where they incorporated reclamation of stormwater and reuse it in the lab. So then we'll have time for Q&A. So just a few announcements before we get started. Hopefully you've all heard by now that we are having our second annual virtual and international education week. It's co-sponsored this year by our European counterpart Egnaton and our Canadian counterpart Sustainable Labs Canada, or SLCan. We're hoping to maybe even add some presentations from Australia and the UK, but through the week of April 15th, you will get all kinds of great insight into green labs, sustainable design, system optimization, and decarbonization. So we're really hoping you'll check out the agenda at i2sl.org/ed-week-2024. Next, we want to remind you that we're also accepting applications for the I2SL Sustainable Laboratories Award Program. And we are lucky that 3 of the 4 speakers on our call today are actually award winners. That's how we learned about their amazing water saving projects. So if you have a project that, or a program or an initiative, or even a team or person that's working really hard for efficiency and sustainability in labs, including water savings, think about applying for or nominating somebody for an award. You have until April 5th to do so. And lastly, just to give it for anyone who's not familiar with the I2SL Circular Economy Community of Practice, it's supported by a 1% for the Planet grant that was given to us through cell signaling technology. And we created a website at www.circulareconomy.i2sl.org, where you can either join as a participant and have access to a little bit more stuff, or just, kind of tour the website and see what we have available. We are having regular forums and webinars on some key key topics that relate to the circular economy. Obviously, in this case, we'll talk about water reuse, but we've talked about expanded polystyrene and what to do with that, how the amount we get in labs, and we'll have some other topics I'll talk about in a moment. Definitely talking about, better, more sustainable purchasing, waste diversion, and other circular economy topics through blogs. You can post a question, post an answer to a question, contribute a blog yourself, make a video and share what you're doing in your lab. Lots of ways to get involved in this community of practice. We really want to make this a two-way street. So check it out at the URL listed here. And finally, just to kind of let you know what the topics are, we created an editorial calendar for 2023 or 2024, sorry, to make sure that we sort of had a lot of different topics. So here are the topics that we're talking about this year. And if something sparks your interest or you have something that you want to share and inspire others to do, please go on the community practice website. There are places where you can submit an idea for a blog. You can even get money to make a video if you have students who are working on a project and they want to give a little what we call Phil Talk. It's like our version of TED Talks. That stands for People Helping Improve Laboratories and gives a nod to our late founder, Phil Wurzik. So please check it out. And without further ado, we'll get into our first forum or our second forum on water. So today we will first hear from Robert Pickering. He's actually my colleague at ERG, but he is an environmental engineer who serves as the technical lead for ERG support for EPA's WaterSense program. He oversees the development of various technical resources to encourage water efficiency, including updates to EPA's WaterSense at Work Best Practice Guide for commercial institutional facilities, which, as I mentioned, helped us create our updated best practice guide for water use in labs. Robbie's also conducted numerous assessments of EPA's labs directly to identify ways for the agency to save water. So he's got some hands-on experience too. So with that, I will let Robbie take it away.
Great, thanks, Kathleen. Are you able to see the slides?
You are not sharing yet.
Oh, all right, let's see. Sorry.
It's okay. Actually, while you're doing that, okay, got it up?
There, does that work?
Yes, now you are sharing.
Okay, great. Yeah, thank you, Kathleen. As Kathleen mentioned, I'm kind of going to give a general overview of what the WaterSense program is, and highlight some of the best practices that I think are broadly applicable to most labs. At the end, we'll share just some other WaterSense resources that are out there to encourage water efficiency. And I'll just say I'm unfortunately the one non-award winner from I2SL, so it only gets better after me. So many of you have probably heard of the WaterSense program. We were launched by EPA in 2006 to really promote water efficiency and encourage innovation in manufacturing of water efficient products. We help organizations and consumers save water for future generations by offering tips to water management, to water efficiency, and changing behavior within the workplace and at home. The WaterSense label, which you can see on the slide, is a simple way that consumers and businesses should be able to identify water efficient products, and on the more residential side, homes and programs as well. WaterSense products and homes are labeled by independent certification agencies, which ensure that they have both water efficiency and performance aspects. We also focus on water saving tips and tricks. So to help specifically commercial and institutional facilities, such as labs, reduce water use and save utility costs, we've released primarily our WaterSense at Work guidebook back in 2012. We've been in the process over the past year and a half in updating that guide, and recently, just I think of 2 weeks ago, published updated sections on laboratory and medical equipment. This also serves as a complement to I2SL's water efficiency guide for laboratories that was released back in 2022. Just to provide a general overview of what I would call typical water use within labs. Certainly this is not meant to be representative of all labs, but is a breakdown of water use within EPA labs that I've conducted water assessments at. So you can see that laboratory specific equipment like steam sterilizers, water purification systems, single pass cooling, and other miscellaneous lab water uses can be significant end users. So and these are mostly unique to lab or medical facilities. So I'll briefly hit on some of the best practices for some of these specific lab water end uses, and then offer some resources at the end where you can go to find out more and do a deep dive into both lab and non-lab specific end uses. So a lot of equipment within laboratories require equipment cooling, and that can sometimes be provided through single pass cooling. So single pass cooling, if present, really has the potential to be the greatest single water waster within your facility. And so when you're kind of starting out with looking at water management, this is a really great place to start. Single pass cooling is a situation where city waters plumb to a piece of equipment to remove heat from it. After use, it goes right down the drain. In laboratories, you might find this associated with air conditioning unit or HVAC equipment, walk-in freezers or refrigerators, ice machines, vacuum pumps, condensers, air compressors, things like that. The hose pictured on the slide is flowing at about 1 gallon per minute, and that's kind of a typical flow rate you might see for single pass cooling systems. At this rate, you're going to be using over 500,000 gallons a year, which will cost you more than $5,600 in water and sewer bills. And this is just taking average commercial costs for water at $10.65. So if you're in a region of the country that's higher water rates or higher sewer rates, which is very common, this type of system can be costing you significantly more. A common use of single pass cooling within labs is for condensers that are typically used in chemistry labs. So condensers are used for synthetic experiments that require reflux and distillation. There are now a few different models of waterless or air-cooled condensers that are on the market. Most water-cooled condensers can easily be swapped out with waterless models, which also provide just kind of a multitude of benefits. Primarily from the water side, you're eliminating that constant stream of water up to 1 gallon per minute. And then as we kind of just discussed, that kind of results in a significant amount of cost savings. Waterless condensers can also reduce the risk of lab flooding, and they also don't require kind of direct connection to a water source. So that frees you up to locate them away from a lab sink or other water source, and it makes the amount of tubing and connection that you need to kind of set these up, it removes that entirely. So actually, Kate Andrews from the University of British Columbia is going to talk a lot about her program to pilot these types of condensers within their university, so she'll be able to speak more about that. Moving on to autoclaves and steam sterilizers. Most lab managers are aware that steam sterilizers are well-known water and energy hogs. They use water in 3 primary ways. First, water is used to produce the steam for the sterilization process. This can usually be either an in-unit boiler or from a centralized boiler system within the lab. Water is also then used to temper the water from the steam condensate that is discharged from the sterilizer. In older systems, this can usually be about 1 to 5 gallons per minute, and this is often running continuously even when it's not needed. This is often controlled by a needle valve that, as time goes on, the flow rate tends to actually creep upward. So even if you think you're using only 1 gallons per minute, or that's what you set it at, 5 or 10 years ago, it's possible or even likely that flow rate is now much higher. So it's good to kind of evaluate that periodically. And then lastly, some steam sterilizers use a vacuum system to assist with material drying. Both liquid ring vacuum pumps and Venturi-based water ejectors both use water in that process. And so this can sometimes add an additional 5 or 15 gallons per minute of water use to these systems. So as far as best practices, first and foremost, I would recommend turning off steam sterilizers when they're not in use, or otherwise trying to program them to turn off at the end of the workday, on weekends, or otherwise during periods where they're just sitting idle. Especially for education and research labs, that they don't really use sterilizers as often as you might think, and equipment can sit idle for kind of weeks on end. So it's really best to just turn these off to avoid unnecessary water and energy use. Another good best practice is to retrofit older steam sterilizer models to include a temperature actuated valve and or a cooling tank to help reduce the frequency that tempering water is applied. A system called the Water Miser is a really popular type of retrofit device. And these systems can reduce water use for tempering by up to 90%, so pretty significantly. And the diagram on this slide actually shows how this system works. I kind of just mentioned inspecting needle valves, but the same exact thing applies to solenoid valves as well. So when you've installed one of these retrofit systems or a solenoid valve to help control your tempering water use, these valves often fail, and when they fail open, which will just return your system to running water continuously. Posting signage or educating staff is really a great way to help identify when these failures occur. And Star Scott from University of Georgia is going to talk about her program and associate user education a little bit later. There's also systems or retrofits out there that are capable of recovering and recirculating water used within the vacuum systems. So look into those if you're looking for retrofits. Also, if your autoclaves or sterilizers are getting up there in age, I would consider looking to replace them. Older models have a lot of these quirks and high water uses, but newer models will typically have built-in tempering water control, built-in water circulation, or at least options to purchase those when you're procuring. The other thing I'll mention about new models is, especially for research labs, really understand and evaluate what your needs are. There's steam jacketed models are really intended for more intense operations where the sterilizer is going to be running all day, every day. But in research applications, as I mentioned, you might not be actually needing your sterilizer as often. So you should consider whether a non-jacketed model that can be kind of booted up as needed and uses a lot less energy and water might be suitable. And then lastly, there might be opportunity to connect your sterilizer to the building chilled water loop as a heat exchanger to help cool your steam condensate and also to generate that vacuum for drying. These systems can also kind of nearly eliminate all the additional water needed beyond just the water to generate the steam. Moving on to fume hood systems. This piqued the attention of Kathleen and a few others on the call when I brought it up. So I thought I'd spend a little bit of time kind of communicating this connection between fume hoods and water use. Laboratory fume hoods can use water both indirectly and directly. So fume hoods with wet scrubbers is kind of the direct use. Wet scrubbers use water to remove contaminants from the fume hood exhaust prior to it being released to the atmosphere. Air that's ventilated through these fume hoods is passed through a water spray or wetted surface. And then during this process, some of the water is evaporated, and some water also needs to be periodically blown down to help control from mineral buildup and contaminant concentration. So this is how fume hoods can directly use water. If they don't have a fume hoods, they still may have a water footprint. Many laboratories use cooling towers for equipment cooling and HVAC. When fume hoods are left open, they exhaust a significant amount of conditioned air, which will need to be replaced with more conditioned air. So, a lot of you are probably familiar with Shut the Sash campaigns, and exactly the same way that you can achieve greater energy efficiency by using variable frequency fume hoods or by closing your sash. Labs that utilize cooling towers should also see an improved water efficiency by implementing these programs. I don't have a ton of time to dive into kind of cooling tower operations and maintenance, but I kind of want to provide a little bit of an overview just so you can understand that connection with fume hoods. Evaporation is the primary function of the cooling tower and is how the heat from the building and from equipment is carried away from the system. Based on the thermodynamics of water, 1.5 gallons of water per hour is needed to evaporate for every ton of cooling, and this number is pretty much fixed. The overall cooling load of the cooling tower then determines the total amount of water that's consumed through evaporation over time. We want this cooling to occur. That's kind of the intent of the cooling tower. So evaporation is really not typically the focus of water efficiency. But with that said, anything you can do to make your chiller plant and your cooling tower more energy efficient will also lower your cooling load, which thereby reduces the amount of water needed for evaporation. So aspects of your facility that can impact this load are building design, envelope design, HVAC design, lighting and plug loads, occupancy, as well as, big fume hoods. So again, in the same way that your shutting the sash can reduce your energy use by reducing this amount of conditioned air, there's also a commensurate water savings that can be achieved through those programs. With that said, some of the best practices to consider. First, if it's safe to do so, turn off your wet scrubber system when it's not being used or when the fume hood's not being used. As I just mentioned, be sure to shut your sash and minimize the air volume being ventilated from the fume hood. This reduces the evaporation from wet scrubbers and the cooling tower, and can improve energy efficiency. Within wet scrubber systems, use recirculating systems for the scrubber fluid, and make sure that any level controllers or makeup water valves are functioning as intended. And then lastly, be sure to control any blowdown from these scrubber systems via a conductivity controller or pH controller, very similar to how you might do that on a cooling tower system, so that they're not just blowing down continuously. Water efficiency should really be the lab's primary focus, but once your systems are all efficient and once you've kind of replaced your equipment and your fixtures, or if those types of replacements don't really make financial sense, laboratories should then kind of turn their attention more towards reuse or on-site collection of alternative water. The one thing to be careful of is just making sure that your water quality needs meet what the intended end use is. Some sources of alternative water include rainwater, condensate from air handler, air conditioning equipment, and reverse osmosis reject water. The air handler condensate is a particularly good use for cooling tower makeup because labs have a lot of dehumidification requirements and pull in a lot of outside air. There's often a lot of condensate that's generated from these outside air units. This is generated in the highest amount in hot summer months when cooling tower demand is also really high. So there's a lot of good correlation between condensate recovery and cooling tower makeup demand. Another good option for labs is looking at reverse osmosis reject water. This can be used for irrigation, for cooling tower makeup, and other equipment cooling. Patrick Murphy will be presenting on a project he has with Lehigh University to talk a little bit about using reclaimed water within their laboratory. I'm over time, and I don't unfortunately don't have time to dig into every piece of lab equipment, but I do want to point to these two WaterSense resources. The first is the I2SL guide on water efficiency best practices for labs that WaterSense partnered on. And then WaterSense at Work also has a lot of really in-depth sections on laboratory and medical equipment that we weren't able to cover today, including glassware washers, water purification systems, vacuum pumps, etc. I'll skip this slide. You can look at it after the fact. And if you have any questions, certainly feel free to reach out to the WaterSense helpline or me directly, and I'm happy to help you improve water management.
Great. Thank you, Robbie. And I did put some links in the chat for the WaterSense at Work resources. Go ahead and peruse those, folks. And if you're done sharing, Robbie, we'll bring Kate up and have her share her presentation. But if you didn't get a chance to get Robbie's information, I know where to find him. So just let me know. So let me introduce Kate Andrews. She leads the Green Labs program at the University of British Columbia, where she brings researchers and operational departments together to advance laboratory sustainability. Her program was named a Green Labs Pioneer by our I2SL Sustainable Lab Awards program in 2023. Kate holds a master's degree in sustainability and energy management from Bocconi University and a bachelor's degree from McGill University. So take it away, Kate.
Okay, can everyone see my slides?
Yes, looks great.
Okay, perfect. Thanks, Kathleen. Yeah, so as Kathleen said, I lead the Green Labs program at the University of British Columbia, and I'm going to talk a little bit about our waterless condenser lending program, as we've called it. Before I start, I'll do a brief land acknowledgement. I'd like to acknowledge that our UBC's activities take place on Indigenous lands throughout British Columbia and beyond, and that UBC's campuses are located on the traditional, ancestral, and unceded territory of the Musqueam and Syilx peoples. So today our agenda is very brief. I'll do a little bit of background and context of our program, our water metering and equipment lending, and then some lessons learned and next steps. So at UBC, we're very fortunate to have some of the best water in the world, but with seasonal rainfall patterns and limited storage in reservoirs, there are periods when water levels run low and water must be restricted. In fact, this past summer, Vancouver experienced level 4 drought, which level 5 is the highest. So really important to be conserving water as much as we can. As a large research institution, UBC consumes an estimated 3.6 billion liters of water per year, or enough to fill 1,500 Olympic-sized swimming pools. And our water use intensity target is a 24% decrease by 2030 relative to 2017 levels. And so, as you know, labs often contain single pass water cooling, specifically condensers is what we're looking at in today, which can use, let's go ahead of my slides, up to 240 liters per hour for a single condenser that's running from the tap through the condenser and then down the drain in most cases. And so we began looking at this. Jeanette Luce spearheaded this project. She was a chemistry researcher at the time, as well as a Green Lab student staff and a member of the Chemistry Sustainability Committee. And so she conducted some preliminary rough water consumption estimates from condensers, and from that, we were able to justify installation of some water metering equipment. And what we found was an estimated 4.2 million liters of water could be saved by replacing these single pass cooling condensers with waterless condensers across, this would be 55 condensers was our estimate, which is approximately 1.1 million gallons a year. And that would mean in Canadian dollars, roughly 6,200 in savings per year and a simple payback of 4.09 years. But we need to test the condensers and gather some user feedback to supplement our proposal for a loan. And so Green Lab fronted some money to purchase some condensers. We purchased two types, the Ascent Condensen and the Radley Spindenser. And so we designed this lending program with these condensers. The idea was that any researcher on our campus could apply to test out these condensers. But in practice, we partnered again with the Chemistry Sustainability Committee, and Jessica, Amani, and Asan helped us to reach different researchers interested in testing them and willing to provide some feedback. So at the 2-month feedback survey point, we do have some lessons learned, fairly high ratings. These are out of 5. For the Condensen, the main difficulties were it was found that the condenser size that we selected was more appropriate for slightly larger scale reactions, whereas many of the reactions run in the labs range from 2 to 20 milliliters. As well, it was commented that they are very tall and can be hard to use. Again, there are different sizes of these condensers that we can maybe test out, but overall worked very well and was very convenient, much easier to set up and more space efficient, easy to use, and no risk of flooding when leaving reactions overnight were some of the findings. And then with the condensers, again, overall, quite high ratings, 4s and 5s, primarily Durability was flagged as a potential concern with worries of being breakable, but I think that may be more a worry than actually anything happening. Other lessons learned, we have all respondents indicated that the water conservation aspect was very important to them, fairly to very important to them, with none saying slightly or not important, which is noteworthy. And then, yeah, in terms of other lessons learned, designing the loan program as available to anyone on our campus, we thought was a good idea in theory, but it did end up working out much better to partner with the existing sustainability committee. They have the on-the-ground contacts and expertise, the relationships, and it worked really well to have them help us out. And so in terms of next steps, we'll plan to launch another survey in another 2 months. That should give us enough context and information to supplement our proposal to a green revolving fund. And it will be important to include, we did not try and quantify the flood risk, but to rather cite this in our proposal as well as a potential cost. And in the meantime, it does look like there's opportunities for us to test out maybe some of the smaller devices for smaller scale reactions. Yeah, and then once we've collected enough data, the plan will be to turn this into a case study that can be used for future researchers, potentially retiring the loan program at some point and distributing the condensers. And so with that, that is my presentation. I do want to thank Jeanette, Jessica, Amani, and Asan for their help, as well as the Chemistry Sustainability Committee in general and the Chemistry Department, and I2SL for inviting me to share. And that
Absolutely, Kate. Thank you for your talk, and a kind of an interesting approach for any of us out there who might be considering equipment switches but can't necessarily sell like a complete retrofit, you know, maybe worth thinking about in other aspects too. So our next speaker, and I'm going to ask her to pull up her presentation, is Star Scott from the University of Georgia. She's the Green Labs program manager there. She's dedicated to making the research enterprise more sustainable and more equitable through her work at University of Georgia. Star is on the I2SL board. She's a founding vice president of I2SL's Georgia chapter and a Higher Education Association Sustainability Consortium fellow. STAR's program received the Outstanding Green Labs Program Award from I2SL's Sustainable Lab Program Awards Program last year. So take it away, Star.
Thank you. Can you see my slides?
Yes.
Perfect. Awesome. Well, thanks so much for inviting me to come share with y'all today. I want to talk to you about autoclave management and a case study at the University of Georgia. So as you know, autoclaves are critical in much of our research, especially our biosafety labs. So they operate at high temperature, under pressure, in order to kill microorganisms and spores. Also, a single autoclave can use as much water in a year as 4.5 American households, and that's if they're functioning properly. So the University of Georgia, we have about 130, give or take right now. So that is a lot of water. Now, autoclaves discharge, and thank you, Robbie, for the setup, and just to kind of refer back to what he already shared with us. But autoclaves discharge very hot water as part of their process. And plumbing code requires that water to be cooled underneath 140 degrees Fahrenheit before it goes down the drain. So discharges that are hotter than 140 degrees, they can compromise the integrity of the drain lines, they can cause leaks or failures. It's very problematic. So to offset this concern, cold water lines are connected to cool the temperature of the water going down the drain. So these are controlled, these cold lines are controlled through a solenoid valve pictured here, the elusive solenoid valve. But anyway, sometimes, as he mentioned as well, they're called a water miser. And in retrofits, we refer to them as water saving kits. But these valves are amazing. They turn on the cold water when it's needed to cool the hot water discharge from the autoclave. But the lifespan of a solenoid valve is around between about 5 and 10 years, in comparison to the lifespan of an autoclave, which is around 50 years or more. I mean, we have older ones at our campus. And when these valves fail, they fail open, allowing cold, potable water to discharge down the drain 24/7, 365. So we added these stickers as part of an educational campaign to teach our users how to listen for and identify failed solenoid valves. So while they're waiting in front of the autoclave for that cycle to finish, they see this sticker and it says a failed solenoid valve in an autoclave can waste 2.6 million gallons of water a year. So if you hear gurgling at the drain when this unit isn't cycling, then give us a call. And so in the first week that we posted these, we got calls identifying 3 failed valves on campus, potentially wasting upwards of 7.8 million gallons of water per year. And so that's about $74,000 worth of water at that time. Now it's a little bit higher. So we were really happy to find these failed valves. But as we dove deeper into our campus autoclave management, what we found was that our campus autoclave contracts were between the PI and the vendor, or maybe in a few cases, the department and the vendor. Some were service contracts with preventative maintenance, some covered parts. They were all totally different. We also learned that that when the vendor discovered a failed valve, their discussion with the PI historically went something like this. You have a failed solenoid valve. It's going to cost between $3,000 and $4,000 to replace, but it doesn't interfere with the function of the unit. So you don't have to replace it if you don't want to. Your unit's going to work fine either way. And so as most of the researchers had no idea what the function of the valve was or is, this is still true to this day, and just how much water it was wasting, many simply chose to save their money and not replace the valve. So on our campus, communication, like the contracts, was historically between the PI and the vendor only. So as Green Labs and Facilities Management Division, which is where our Green Labs program is housed, we weren't the customer, so we weren't really able to play, or get in the mix at all. We couldn't do preventative maintenance. We couldn't even check these units without potentially compromising those individual service contracts, which of course we didn't want to do. So as you can imagine, this was extremely problematic because facilities was paying the bills for this wasted water. All right, so like any good cooking show, I'm just gonna fast forward to my final dish and just pull it out of the oven right now. UGA, we assembled a multi-stakeholder team for autoclave management, and this is who it includes: Utility and Energy Management, Green Labs, the Office of Research, the vendor, and then of course end users, because they're absolutely critical for actually identifying the failed valves. And then Utility and Energy Management offered to pay for any failed valves that we found, as the cost of that repair was minuscule to the cost of the water wasted. So the vendors get paid, facility saves money, water is saved, most importantly, and end users know that they really make a difference. So now we have this unified team approach on campus, which includes facilities in the conversation, which is very important. And it also includes, of course, the financing to repair these units. So thus far, since we've started this, we've identified 8 failed valves, each wasting potentially 2.6 million gallons of water a year, which is around 20.8 million gallons of water. That's around $200,000 of clean, potable, life-giving water. So we're really happy about that. One last thought I want to share with y'all today is just this process really is working for us now. However, for those of you who might have the option, if you have an option of a singular campus-wide service contract with your vendor, that would be even more efficient and even more functional. And so just to end, I want to share this totally unrelated but super adorable fruit bat with you, and a QR code if you want to reach out or you want to check out our program. I'm happy to engage with anybody who wants to do so. So thanks for having me.
Awesome, Star. Thank you. Thank you for a lighthearted approach to a controversial topic. And I'm only wish you taken the opportunity to call your presentation. It's the great autoclave Charlie Brown. But other than that, I think you're spot
Oh my
on.
God, that would have been perfect. Thank you.
And that reminded me, thank you for like telling us this simple tip of listening for the gurgling sound. This is Fix a Leak Week, by the way, that WaterSet celebrates every year, the third week of March. So if you're in your lab, walk around and listen for the gurgle near the autoclave, and maybe you can fix a leak too, if you have the right contracts in place. So thank you for that. Our final speaker is also an award winner for a building in the buildings and projects category for Lehigh University. And this is Patrick Murphy from Vanderwild Engineers, and as Director of Sustainable Design for the company. Patrick is leveraging his passion and experience in sustainable, integrated, and innovative building design to inform and designs through rigorous energy and water analysis. His background as an architectural engineer with a focus on sustainable MEP systems informs his multidisciplinary and collaborative approach to laboratory design. So let's hear about one of their designs at Lehigh.
All right, thank you. So our project. All right, our project at Lehigh University just opened recently. This was a brand new college for Lehigh University located in Eastern Pennsylvania, a new college of health. I want to give a little bit of context before we get into some of the water story. This team, which was led by HG Architects and Vanderwild Engineers, really took a data-driven approach to our design to analyze all of our design decisions, model them, and make sure that we're making our choices consciously. That included energy modeling, also daylight modeling, and we also developed a whole building water mapping tool, which I'll get into in a little bit. This being a new college of health, we sensed an opportunity from the first meeting with the university. We brought up the concept of wellness design, that the effect that our buildings have on us, because we spend 90% of our hours alive in buildings, is tremendous. And by having that conversation early, we're able to incorporate strategies that wouldn't otherwise have been able, to be incorporated into the design. That included things like active design, encouraging people to use the stairs instead of an elevator. Also included a lot of biophilic design elements. These are elements that either directly or indirectly connect the users with nature, which has documented health benefits. What that means for a water story, we were focused on water quality, access to drinking water. Also, we had plants throughout the building for that connection to nature. You see some of them in these images. And, that was just one theme of the project. Otherwise, we were taking a relatively, a progressive approach to energy consumption and things like that. This building was a brand new, very large building on campus. And the first question the team was confronted with was the utilities to serve the building, whether they could support this large new infrastructure. And so we did a study in conceptual design around whether the campus central heating and cooling plant could even support this building. And all the different combinations of cooling centrally, heating locally, or vice versa, or everything locally, or everything centrally, and do we use an air-cooled chiller or water-cooled chiller? Lots of different combinations, which is what the table at the top was trying to depict. Hard to keep track of, so we had some fun with colors. But for the water story, we were sensitive to water consumption. Eastern Pennsylvania may not seem intuitively, but it is a relatively water-sensitive region, and the areas that are circled, the system options that are circled required no water use for cooling. They eliminated the cooling tower altogether, which is pretty dramatic, both from a water savings perspective, but also from a maintenance perspective. The cooling tower, especially being located outside their central plant somewhere else, was something that the university was concerned about having to maintain. We took a holistic approach to water use in the building. Now, this graphic is not, unfortunately, the graphic of the water use in this building, but I'm going to use it to illustrate a point. We think about the supply of water for the building, and it's not just the municipal water supply. We're generating water within the building. The condensation coming off of our cooling systems is one of them. Also, we're collecting rainwater that hits the roof or hits the site, and we have to do something with that. Those are opportunities to use water within the building. Our demands, in a traditional lab, there's cooling towers associated with the cooling systems. You have your plumbing fixtures in the building. If there's any kind of kitchenettes, and this project actually had a cafe, there's water consumption associated with that, and sometimes irrigation as well. Like we had the irrigation both for our external plants and also for those internal plants. And then finally, our discharges. Where does that water go once it gets used? Some of it gets evaporated into the atmosphere. Some of it goes down the drain to be treated by the municipal sewer system, and some of it goes to the storm system. By mapping out and thinking, contextually about the entirety of the water use and where it comes from and where it goes in a project from the beginning, you start to see the connections, where you can close those loops or recycle water back. So as confusing as the spaghetti of arrows may be, kind of in the left, we're showing that you can use that HVAC condensate and that roof rainwater with some, relatively modest level of treatment and use it for cooling towers or use it for irrigation. And that was kind of a starting point, a best practice to responsibly use stormwater on the site and reduce the water consumption in the project. But remember, we were also really focused on that cooling tower water use. So the baseline building, the typical building, like code baseline or lead baseline building, it uses water in there's a seasonality to the way that it uses water. There's a year-round pretty steady use of your plumbing fixtures and your laboratory fixtures and process water use, which is at the bottom in orange there. But then we see this very, dramatic seasonality to irrigation and cooling tower water use, peaking in the summer. The donut chart on the right quantifies for our project, we eliminated irrigation altogether, the need for outdoor irrigation altogether. But the rest of the, the loads, what's readily apparent is that it's the cooling tower that is the biggest water use. And we always, we focus on process water use, or we focus on, our plumbing fixtures or things like that, which are important. And I'm really glad to hear the conversation today up until that point. But really, the cooling tower is this opportunity where the energy and water come together and have this dramatic impact. A cooling tower works by evaporating water into the atmosphere to cool it down, and that's part of your cooling system for the building. But there are other ways to cool a building without using any water at all. And also, we can take approaches that reduce the cooling load in the building in the first place, so we don't have to evaporate as much water when we are using those systems. So that was the approach that we took. And our proposed design we ended up pulling all the equipment, the heating and cooling equipment into the building. We eliminated the cooling tower altogether. It was such a dramatic impact on maintenance and also on water consumption. We just did without it. So we used what's called an air-cooled chiller instead. So we were just exchanging that, rejecting that heat to the atmosphere with no water evaporation. It's a little bit less efficient from a cooling perspective, but it has its benefits, certainly on the water side. So you're seeing we just chopped the top of that water mountain off. And that allowed us to have some pretty dramatic savings. Then when we're collecting the roof rainwater and the HVAC condensate, well, now we need to do something with it because we eliminated that cooling tower altogether. And so since we don't have any outdoor irrigation and the indoor irrigation, it's not that much. And so we need to do something with that water. We used it for toilet flushing. So with some additional treatment, we used a system that delivered non-potable water for our non-potable needs within the building. The labs and the lab processes still get potable water supply, and we're conscious about using that efficiently, but we're eliminating potable water demands where we can. In total, the effect was that baseline used about 6.5 million gallons per year. The proposed design reduced that to 1.5 million gallons a year. And that's enough water to fill Lehigh's swimming pool for their swim team 30 times a year. So pretty dramatic savings. And the two main strategies that we used were eliminating the cooling tower and by recycling or reclaiming that roof rainwater and HVAC condensate to use it for some of the loads in our building. This is the final product from the south side. There is a screen on the south side. We were conscious of reducing our cooling loads, but some of the highlights in the end, close to 45% energy savings, 76% total water savings, and EUI of about 132. Project achieved LEED Gold. And also remember that it's a wellness design centered building. There's a certification for that. There's actually a couple of them. We pursued Fitwel, and Fitwel awarded it its highest rating, 3 stars, and actually gave this project an award for the highest scoring project in the world under the Fitwel system when it opened last year. Now, just to pivot a little bit, coincidentally, this being Water Week, I just ran here from a conference. I gave a keynote at a conference in Boston on water resilience earlier today. And the highlights, the two highlights from that are water is the primary medium through which we will feel the effects of climate change. We see it with the increased, stormwater events or even like snow we're seeing in the Sierras. We're also seeing in the terms of droughts. The extremes are that much more, and it's manifesting through water. And so the conscientiousness that we have about not just our emissions or our energy use, but also water are critical to, our short-term and long-term design around climate change. And so by taking this holistic approach, like I just showed you on Lehigh, which is called a one water approach, which is a transformative way of viewing, valuing, and managing water, looking at it holistically in an integrated system, which, we had the benefit of starting from scratch with a new building. That allows you to have this really dramatic impact, but you have to have the right mindset about that. So that was really our message to this community at this conference. And hopefully, something that will be inspiring for you as you're working on, your next buildings on campus or major renovations. Thank you.
Great. Thank you so much. If I'll ask everyone to turn their camera on, we can answer a few more questions. And thanks for wrapping up on that note, Patrick. I think that gives us all sort of an inspiration and reason to keep working on this issue. We do have a few questions in the Q&A. I'm going to try to get to first. If we have time, I'll ask a few panel questions. The first one is for you, Patrick. Was there a savings between water reduction from the tower elimination versus the energy usage of the air-cooled condenser?
Yeah, that's an interesting point. There was actually an energy penalty for going with the air-cooled chiller instead of a traditional water-cooled chiller. The evaporative process is just inherently more efficient from an energy perspective. We compensated for that. So we took the hit on using the air-cooled chiller, but we compensated for it within our building with energy recovery strategies. We used chilled beams. There were a lot of strategies to reduce the cooling load, that screen on the south facade, to reduce the cooling load so that we didn't need to use as much cooling inefficiently, just to kind of counteract that.
Okay, great. Our next question, we have a couple that are related, Star, to your autoclave talk, and I'm going to start with one that's about the discharge water, but then we can also kind of get into the condensate as well. So if you may have commented on this already, but can you elaborate on if the hot water that is discharged from the autoclave, is it able to be repurposed in another aspect besides going down the drain, like directed to hot water use in campus housing or laundry facilities?
Oh. That's a great idea. I have not heard of the discharge water being utilized in that way or diverted in that way. Robbie may have some insight to that I don't have. Our system, we're a 200-year-old institution, and most of our autoclaves on campus are pretty old. And so that technology might exist now, But certainly I think it would require a lot of infrastructure changes, which I don't know that we're able to do at this time, but it is a great idea. Robbie, have you ever heard of that?
Yeah, essentially it works the same as like your typical like boiler trying to heat recovery. So similarly, if you blow down your boiler, there's heat in that boiler blowdown, and you can recover that for preheating either a boiler makeup or another purpose for like that was mentioned for hot water use or laundry. The challenge that I'll just echo from what Star said is that a lot of these autoclaves are just kind of plumbed to floor drains wherever they were put, when they were first installed. And so, it may not be in the exact place that you actually need that heat, elsewhere in the lab or, so yeah, the challenge with a lot of, including water reuse projects as well, is just, a lot of these buildings are already built. So trying to get the plumbing, and the infrastructure to support those, can be expensive.
Sure. And we had an idea from Mark, one of our attendees, who's found considerable energy and water savings by recovering the autoclave jacket clean condensate instead of dumping it to the drain. It's clean condensate, not in contact with the media. Also an idea to put autoclaves on schedules to shut down after hours to keep from wasting steam and water, if anyone wants to talk about that a little bit.
Sure, I'll jump in. I actually replied to him and asked if he was talking about the drain water tempering discharge, or if he was talking about the condensate. I was curious if he had a system for recover for the drain water discharge. That's really awesome. As far as turning them off and on, so many of our units are these old monster units. They look like a vertical washer dryer system. They're about that size. These systems that have been on our campus for a very long time are really actually not right sized to our needs. So they were meant to be used in industrial settings, running 24/7, 365. In our setting, we audited the logs on these units. We saw that they were being used at maximum about 6 cycles per day. So that's a lot of downtime, but unfortunately they weren't designed to be turned off and on. And that was information that came from that manufacturer, who said, if you turn it off and on, the heating and cooling of the pipes loosens the fittings, and over time leads to leaks and inefficiency in that system. So we were actually advised by the manufacturers not to turn those off and on. Honestly, UGA would, our future, we'd love to move away from those jacketed autoclaves. We would love to move towards electrification of our autoclaves. There's some incredible technology that exists right now that saves a tremendous amount of water and energy for these units. And hopefully that's in our future, but not our immediate future.
Got it. Yep. Always trade-offs. One last question I think we have time for with regards to water reuse, Patrick or Robbie or anyone else who wants to comment. For water from AC or condensate, if it may contain pathogenic organisms, are there biosafety concerns when you're considering water reuse?
So one of the benefits that we have in lab facilities on this might not always be a benefit, but we're capturing the vast majority of that condensation from our outside air. So it's already fresh air. It's not contaminated air. Now, we also have water that we're collecting from like fan coils within labs. And there you might have to be a little bit more careful, but the vast majority of the condensate that we're collecting is coming in the 100% outside air handling units, and that's clean.
I would also say that the traditional way of managing cooling towers is through various forms of chemical treatment. So your cooling tower to be managed usually has some sort of biocide in there, some corrosive control, some scale control, and so those chemicals are kind of already in in the system, and so any condensate you're adding is already pretty cool in clean water. But if there is any kind of risk of that, it'll be taken care of by your chemical treatment. These days there are non-chemical treatment options for cooling towers, so maybe that's the asterisk to my statement. But as Patrick mentioned, if you're collecting this from outside air handler units, it's really clean water coming in. There's not a lot of opportunity for nasty stuff.
Great. All right. Good to know. Well, I think we need to wrap up and let everybody get back to checking for leaks around their labs. And I want to really thank our amazing speakers today for giving us lots to try and think about. So please join us again soon. Thank you.
Thank you.
Thank you.